Hello everyone. Today I'm going to present on Fourier's law, the fundamental principle governing heat conduction in materials with special focus on its application in food processing. This is part of our heat and mass transfer for food processes course, unit 1. Let's begin. Fourier's law is the cornerstone of heat conduction. It tells us that the rate of heat transfer through a material is proportional to the negative temperature gradient and the material's thermal conductivity. In simple terms, heat always flows from hot to cold regions. This law helps us predict how the heat moves in solid foods and processing equipments. By the end of this presentation, you will be able to understand the mathematical formulation for Fourier's law. So, explore its practical use in cooking and food process. First, let's comprehend the basic formulation. Fourier's law is expressed as Q is equal to minus K delta T. Delta T is nothing but dt by dx, where Q is the heat flux, K is thermal conductivity, and dt by dx is the temperature gradient. In food industry terms, this helps us calculate how quickly the heat penetrates a dough in a baking tray or a liquid inside a can. Different materials have different K values, different K, where K is the thermal conductivity. So each kind of material has its own thermal conductivity. Thermal conductivity is nothing but the ability to transfer the heat or electricity through its material, through its body. So the metal conduct heat fast while the food materials like dough conducts it slowly. In practice, the Fourier's law is crucial in the food industry. In baking, it explains how heat spreads evenly through trays to achieve uniform browning and texture. In canning, high thermal conductivity of metal allows rapid heat transfer to sterilize the contents. So, understanding this improves cooking efficiency, reduces energy use, and ensures food safety. Here is the law explained visually. The equation minus k delta del t is essential for engineers, particularly food engineers. In food processing, we use it to design ovens, retorts, and heat exchangers. For example, in baking trays, heat conductivity means faster and more uniform heating, which directly impacts product quality. Physically, heat conduction is energy transfer due to the molecular collisions. No bulk movement of matter, temperature gradients drive this flow. In food applications, baking trays distribute heat evenly to avoid hot spots, while metal can transfer heat rapidly during sterilization. This affects the cooking time and final product quality significantly. Let us look at some real life examples. Heat conduction through a coffee mug wall. Why the outside feels warm? Living in an igloo. Snow's low conductivity traps heat inside. And heat transfer in cylindrical pipes. So important for steam line in food plants. And heat loss through a window, similar to heat loss from ovens. So all these illustrate Fourier's law of action, Fourier's law of heat conduction in action, and connect to food processing scenarios. Thank you.